طلبة المرحلة الخامسة، السلام عليكم ورحمة الله. نكمل بإذن الله مواضيع مادة Therapeutic Drug Monitoring، وموضوعنا لهذه المحاضرة هو Concepts in Pharmacokinetics. To assess the metabolic activity, an equation which is called Michel's-Menten equation can be used. Before that, we should understand that enzymes in the body that are responsible for metabolism are proteins, and each tissue has a specific amount of these proteins. For the action of enzymes, I guess you know that the substrate should be conjugated with the enzyme, and then the metabolic activity or the metabolism will occur to a drug or the substrate. The metabolic enzyme concentration is constant, as we said, at a given site, and the drug, which is the substrate concentration, might be vary, which means if we have a low concentration of a drug, it might not saturate all the available active substrate sites in the enzymes. And if we have a high concentration of a drug, it might saturate all the available digestive or enzymatic sites. When a drug concentration is low relative to enzyme concentration, then the rate of metabolism is a first order process, which means as the concentration increases, the metabolic activity will be increases, while at very high plasma concentration, the process then becomes a zero order. This is because, as we said, there is a specific number of available sites for the metabolic activity. If all of these sites are saturated, then the rate of metabolic activity will depend on the function of only on the function of available sites, and increasing the concentration will not increase the metabolic activity. This can be shown here in this figure, where the x-axis represent the substrate concentration or the drug, and the y-axis represent the velocity at which the metabolic activity occurs. At the initial points, increasing the concentration of a drug will definitely increase the rate of or velocity of metabolism. That's why increasing the concentration will increase the metabolic activity until we reach a point where the drug concentration is very high, and then this will saturate all the available enzymes for metabolism. Then increasing the concentration will not increase the metabolic velocity. That's why we reach a place where increasing the concentration will never increase the metabolic activity, or this case we call it a plateau, or the maximum velocity of metabolic activity. At a concentration of a drug that gives half of the maximum velocity of metabolism, this concentration of a drug is called Km, or Michel's-Menten. As we said before, Vmax represents maximum reaction rate, and Michel's-Menten constant, or we call it composite parameter, can be defined as the drug concentration at which the reaction occurs at half the maximum rate. The relationship between Vmax and Michel's constant is given by Michel's-Menten equation for first order kinetics. At the cases where increasing the concentration of a drug will definitely increase the rate of drug metabolism, the equation can be written in this way, where the Vmax is multiplied by plasma concentration over Michel's constant plus plasma concentration equals to the rate of drug metabolism. In the case of first order kinetic, the value of drug plasma concentration is much less than the Km. Therefore, the equation can be rewritten as Vmax multiplied by plasma concentration over Km. Since Vmax and Km are constants, then increasing plasma concentration will increase the rate of drug metabolism. In the other case, in zero order kinetics, the equation can be written like Vmax multiplied by plasma concentration over Km plus plasma concentration. Since plasma concentration in cases of zero order kinetic is very high, therefore we can just neglect the value of Km, and the equation can be rewritten as Vmax multiplied by plasma concentration over plasma concentration. Plasma concentration can be omitted with this plasma concentration, and therefore the rate of drug metabolism will equal to Vmax, which is a constant despite the change in plasma concentration. This is also present the rate of drug metabolism with drug doses. For first order kinetic, we know that increasing plasma concentration will increasing drug concentration will increase the rate of drug metabolism, but for when we reach a very high concentration, the rate will not be increased. An example for drugs that can reach zero order kinetic process is are aspirin, ethanol, and phenytoin. The doses are very large, therefore plasma drug concentration is much greater than Km value, and drug metabolism is zero order, that is constant and independent of the drug dose. By the way, even for these drugs, at initial concentrations where the concentration is very low, the process of metabolism can be described as a first order elimination of process, but when we reach a higher doses, which is common with these drugs, no, we will reach a zero order kinetic process. Okay, so how metabolism of drug occurs inside the body? You might know that there are two phases for drug metabolism. We normally call it phase 1 and phase 2. Phase 1 represents the processes that occur due to oxidation, reduction, or hydrolysis, and phase 2 is normally conjugation of water soluble component that resulted from the phase 1 metabolic activity. And usually phase 1 normally converts the metabolized drug to a more hydrophilic component that can be easily conjugated in phase 2 with a molecule that facilitates the excretion of this drug. It's not necessary that the drug should pass through both of these steps. It might only pass through phase 1 processes, and also it might also pass only through phase 2 metabolic processes. Phase 1 reactions involve the activity of cytochrome P450. This cytochrome P450 is we call it sometimes mixed microsomal mixed function oxidases, which represent a superfamily of heme-containing isozymes that is differ in the nomenclature between each other, and this superfamily are similar by 40% with each other, and the subfamily are 70% similar with each other. Differences. An example of one of the isoenzymes of this superfamily is cytochrome P3A4, which is one of the largely distributed subenzyme of this family. It is also distributed in the intestinal mucosa and can cause a metabolism of drug within the intestinal wall. An example of drugs that are metabolized by cytochrome P3A4 in the intestinal mucosa or intestinal wall are chlorpromazine and clonazepam. Anyway, for the nomenclature of this superfamily, after the symbol CYP, 3 represents the family, A represents the subfamily, and 4 represents the specific protein of this family. The distribution, as we said before, cytochrome P3A4 represents the largest member of this mixed function oxidases superfamily. Therefore, it is responsible for the metabolism of most of the drugs in the body. Polymorphism is a phenomena that may cause differences in drug metabolism. You can see here in these two pictures a jaguar, which both of them are biologically similar, but they show differences in shape. Same can apply to metabolic activity of enzymes, despite the fact that humans are similar in biological components, but the activity of these enzymes might be different from a patient to patient or based on races of these patients. Like a patient from China is definitely different in the metabolic activity from a patient in the Middle East, or even in the same family. A patient has a rapid metabolic activity while the other has a slow metabolic activity. And most of an example here for the different activity of or change in the activity of enzymes is that, for example, there's a polymorphism in cytochrome P2D6 which affects the codeine metabolism in patients. Also, there is a polymorphism in cytochrome P2C which is responsible for the metabolism of clopidogrel. Also, drugs might affect the metabolic activity of enzymes, like in addition to polymorphism, in addition to that metabolic enzymes might be different in metabolic activity, other drugs can affect the metabolic activity for an enzymes. Like here, the metabolic activity of the enzyme 3A4, which is, as we said, metabolizes most of the drugs, like around 50% of the drugs. The substrate is very long list of substrates. There is a drugs that can induce the activity of these enzymes like barbiturate, rifampicin, phenytoin, carbamazepine. These drugs then can enhance the metabolic activity of the enzymes and the enzyme, and therefore increase the metabolism of the substrates. In this case, when we co-administer a drug which is metabolized by cytochrome P3A4 like cyclosporine, and then we co-administer with it a rifampicin, then we should consider that the drug will be rapidly metabolized and the resulted plasma concentration will be lower than expected due to enhancing the metabolic activity, and therefore the concentration in the plasma might be lower than the minimum effective concentration, or the concentration in the plasma will be subtherapeutic, and therefore this can cause a failure in the treatment of the drug. In other cases, where a drug which has an ability to inhibit the metabolic activity of this group of enzymes, like erythromycin, ketoconazole, fluconazole, grapefruit, or ritonavir. When these drugs are co-administered with one of the substrates, then the plasma concentration of the substrate might be higher than expected, or sometimes the plasma concentration might exceed the minimum toxic concentration, and therefore might cause toxicity or adverse effects due to this drug interaction. In other drugs, the inducers and inhibitors for the enzymes are small list compared with the inducers and inhibitors that affect 3A4 enzyme. Pharmacokinetic models are normally applied to calculate pharmacokinetic parameters like volume of distribution, clearance, half-life, elimination rate constant, or even to calculate doses or plasma concentrations at different times. Three pharmacokinetic models are normally applied. These are compartmental models, which consider the body the body is composed of one or more compartments. And also we have the non-compartmental analysis, which does not consider the body composed of compartments. And we have the more specific physiological models, which consider each part of the body, each organ of the body, as a single compartment which has its own extraction ratio, flow rate, and distribution. Compartmental models are most commonly employed approaches to the pharmacokinetic characterization of a drug, which consider the body as a system of components. By the way, these components usually have no physiological or anatomic reality. In one compartment model, which is the model assumes that the body can be described as a single uniform compartment, and the drug can enter and leave the body. In the one compartment model, the input of the drug can be first order kinetic, like in case of the drug absorption from the gastric tract, or zero input of a drug like infusion, or even IV bolus, direct infusion of the drug or direct injection of the drug. And usually the elimination or the exit of the drug from the one compartment system is a first order kinetic. As we said before, this compartment model consider that the drug is uniformly distributed within the one compartment. But this does not mean that the concentration in the plasma is similar to the concentration in liver, brain, or kidney, or muscles, or even fatty tissues, but they usually exist in equilibrium, which means that the rate of transfer of drug from plasma to muscles is equal to the rate of transfer of drug from muscles to plasma. And despite the fact that the amount of a drug in muscles could be larger or less than the amount of a drug in a plasma, and this depends on how the drug is binded to plasma proteins or tissue proteins in different compartments or components. Okay, so we start with one compartment model in case of IV bolus administration. Following IV bolus administration, it assumes that the drug is administered instantly into the body. It is instantaneously and rapidly distributed throughout the body. The equations that can be used to calculate the plasma concentration following IV bolus administration our plasma concentration at any time equals to plasma concentration at time 0 multiplied by e to the power minus elimination rate constant multiplied by the time. As you know, initial plasma concentration equals to the dose of a drug over volume of distribution. So the equation can be rewritten in the form of plasma concentration at any time equals to dose over volume of distribution multiplied by e to the power elimination rate constant by the time. By the way, some of the drugs are should not be administered as a IV bolus in very short time. And sometimes they need around 5 to 30 minutes to be injected into the body by IV bolus. So for these drugs, if the elimination rate constant of these drugs is large, then the eliminated amount of a drug during the infusion period, the short infusion period, will not lead to a larger amount of the drug to be eliminated, which means that we can still use IV bolus administration equations to calculate the plasma concentration of such drugs. We take an example to the calculation of a plasma concentration of a drug which was administered by IV bolus. Assume that a patient is given a theophylline loading dose of 40 mg intravenously over 20 minutes. It's known that the volume of distribution is 30 liter and the elimination rate constant is 0.116 per hour. compute the expected theophylline concentration 4 hours after the dose was given. Theophylline follows one-compartment model, pharmacokinetic. Okay, for the solution we should calculate the elimination rate constant. The elimination rate constant, sorry, the half-life. The half-life can be calculated by dividing 0.693 over the elimination rate constant. Then the result will be 6 hours. You can see here that the drug was intravenously infused over 20 minutes. But the half-life of the drug, is large compared to the infusion time, and then the drug loss within the infusion time or the drug elimination within the infusion time will be very small, and we can neglect this small amount of eliminated drug during the infusion time and consider that the drug was administered by IV bolus processes, and then we can use IV bolus equation for the calculation of a plasma concentration as follow. Plasma concentration at any time, we have the dose here, which is 40 milligram, and we have the volume of distribution, which is 30 liters, and we have the elimination rate constant, and the time which is required here in the question, which is 4 hours, and the result will be 8.38 milligram per liter. Okay, another example in which a patient is given an intravenous dose of vancomycin 1000 milligram over a period of 1 hour. It is known that vancomycin takes half to 1 hour to distribute to tissues, which means that the drug follows a two-compartment model of pharmacokinetic. If you know that volume of distribution equals to 50 liters and elimination rate constant is 0.077 per hour, calculate the expected plasma concentration of vancomycin 12 hours following the administration. Okay, again, we calculate the half-life of the drug, which is 9 hours. You can see here the intravenous infusion time plus the distribution time is very short compared with the half-life of the drug. Therefore, IV bolus equation can still be used for the calculation of plasma concentration of vancomycin. Here we should just compare the half-life of the drug with the infusion or the distribution time. Usually, if a drug has a distribution and distribution or administration time within 1 hour and it has a large half-life, then it's easy to calculate the calculate plasma concentrations using using equations of IV bolus. Again, here we just apply the equation and we can get results of plasma concentration 12 hours following this administration, which is equal to 7.9 milligram per liter. But keep in mind, we cannot calculate plasma concentration within the infusion time using this equation because the drug is not homogeneously distributed, and one compartment open model equations cannot be applied in this case. Okay, so calculation of pharmacokinetic parameters from plasma concentration time curves. Sometimes we don't have an information about the elimination rate constant or the other pharmacokinetic parameters for a drug. But if we have a patient in the hospital and we have a machine or an HPLC, like an HPLC or other machine to calculate plasma concentration of a drug, we can simply calculate two or more plasma concentration time points from the patient, and then we can calculate the pharmacokinetic parameter of a drug like half-life and volume of distribution. This can be done by two methods. First is plotting the plasma concentration time data on a semilogarithmic paper. In this, the steps to do this is first determination of half-life using the plot. We can choose a concentration and name it concentration 1, and then determine half of this concentration, half of this concentration on the plot, and the time interval between the C1 and half of C1 represent the half-life of the drug. And then we can simply calculate the elimination rate constant from the half-life. So this is the semilog paper. You should remember it that the the y-axis represent plasma concentrations in logarithmic scale, and the time on the x-axis. We can, if we have 2 points or more, we can plot the plasma concentration time curve should appear as a straight line. If we just take a 1 point here, consider that the first point is 12.5, then we just half this concentration, and we should plot a point at 6.25. This point should come on the straight line that we draw it from the two initial points, and then the reflection of this concentration to the time axis, and we calculate the interval between the first point and half of the first point. In this case, the time interval is 1 hour, which means that this drug takes 1 hour to decrease by half, which is the definition of half-life of a drug. So the half-life, as a calculated from this figure, is 1 hour. Okay, so for the calculation of volume of distribution, again we can extrapolate the straight line that we got on the semilog paper to intercept with the plasma concentration or the y-axis. So the intercept of this straight line with the y-axis represent plasma concentration at time 0, and therefore we can calculate volume of distribution simply by dividing the dose over the concentration that we got from the extrapolation of the straight line. Okay. Also, we can do calculations without plotting the concentrations. And in this case, we calculate the elimination rate constant by determining the slope. We still need at least 2 points of plasma concentrations to be able to calculate elimination rate constant and half-life, as well as the volume of distribution. In case that we do not need, or we do not want to calculate the elimination rate constant and the volume of distribution by the plotting technique, we can just use the slope technique in order to calculate the elimination rate constant. In this case, the slope, as you know, equals to change in the values of the y-axis over change. So this should read x-axis, and then the change in the values of the x-axis, which means y2 minus y1 over x2 minus x1. Keep in mind that y values should be in logarithmic, should be converted to log values. And then in this case, we can just calculate the slope, the elimination rate constant, since the slope equals to minus k over 2.3. And also then we can calculate the elimination half-life, which is 0.693 over elimination rate constant. For the calculation of plasma concentration at time 0, we can rearrange the equation for the straight line. So the equation of open model, IV bolus of open models, which is plasma concentration at any time equals to plasma concentration at time 0 multiplied by E to the power minus elimination rate constant multiplied by time. Then in this case, plasma concentration at time 0 equals to plasma concentration at any time. And then here we should put one of the points that we got from the calculation of measurement of plasma concentration, and then over E to the power elimination rate constant that we calculated from the first step, and then multiplied by the time at which this plasma concentration was taken. Okay, so let's take an example to to calculate volume of distribution and the elimination rate constant using two techniques, plotting and non-plotting. A patient was given an intravenous loading dose of phenobarbital 600 mg over a period of about 1 hour. 1 day and 4 days after the dose was administered, phenobarbital serum concentrations were 12.6 mg per liter and 7.5 mg per liter respectively. This means that 1 day and 4 days, 1 day after the administration, which is 24 hours after the administration, the concentration, plasma concentration was 12.6 mg per liter. And 4 days after the dose was administered, plasma concentration was 7.5 milligram per liter. Here, calculate elimination rate constant, half-life, volume of distribution by plotting data and by calculations without plotting. Okay, so by plotting the data, we should consider that the time here in days, and we have the concentration of a drug 1 day after the dose was administered. Here, the 1 day was 12.6 milligram per liter. And also we have 4 days following the administration, which is 7. So this point is 7.5 milligram per liter. We draw a straight line between these 2 points because we have used a semilog paper, and following on the plasma concentration time curve on a semilog paper, if it follows a one compartment model, should be a straight line. Then we have a straight line here. Okay, so now we should calculate the half-life by using the plotting. This can be done by dividing one of these points, either this one or this one, the 7.5 or the 12.6, to half, and then find the time interval between this point and half of it. In this case, 12.6 is divided to 2, and then the concentration will be 6.3. So this can be done by simply by extrapolating the line, the straight line, and then determining the plasma concentration 6.3 from y-axis to intercept with the straight line, and then we find the time of this point here. The time of this point is 5 days. So the time interval between half the concentration and the initial concentration is 4 days. According to this, the half-life of the drug is 4 hours. We can just simply calculate the elimination rate constant based on these calculations. Also, to calculate the plasma concentration at time 0, we extrapolate this line to intercept with the y-axis. Here, according to this, the intercept with the y-axis gives a value of 15 milligram per liter. So the initial plasma concentration is 15 milligram per liter, which can just divide the dose over the initial plasma concentration to get the volume of distribution. And for the calculation of the parameters without plotting, you can apply at home the equations, and you should be able to get the same or quite similar result as those that we calculated by the plotting technique. Okay, so now we consider the IV intravenous infusion technique for drug administration. As you know, it is common practice in the hospital setting to infuse a drug at a constant rate or constant input. In this case, it's zero order input. This method permits precise and readily controlled drug administration. The infusion rate of a drug is controlled by the flow rate of the drug from the IV set infusion. As you know, in the hospital, we can set the infusion rate as ml per minute, ml per hour, or as normally we do, number of drops per minute, and then we calculate number of mils per minute or per hour according to the concentration of a drug and the required plasma concentration. So for the determination of infusion rate, we should know the flow rate, which is normally per volume, units volume per hour, per unit time, and also we should know the concentration of a drug. And in this case, the concentration of a drug can be represented by mass per volume or weight per volume, according to our calculations. Initially, the rate of a drug, we can just show the pointer. Initially, the rate of at which the drug enters the body, although constant, is greater than the rate at which drug is eliminated. So there will be an accumulation of drug through the initial time points of drug administration. This will allow accumulation of drug until we reach a point at which the amount of drug that is infused is equal to the amount eliminated, and in this case we reach a constant plasma concentration. We call it a steady state plasma concentration, at which rate in equals to rate out. So again, in the initial first point, the amount of drug infused is more than the amount of drug eliminated, or the rate of drug infusion is more than the rate of drug elimination. Here, this will cause an accumulation of drug in the plasma. The accumulation appears as an increase in the plasma concentration with time until we reach a point at which the rate of drug in equals to the rate of drag out, and in this case we reach a steady state plasma concentration. Okay, to monitor the drug in the plasma or serum following IV infusion, we have two cases or two situations. The first is during infusion time. During infusion time, we can monitor the plasma concentration, and then we can do monitoring for plasma concentration post infusion time, which means following the cessation of infusion. Okay, so during infusion time, the concentration of a drug in the blood is determined by the following equation, which is plasma concentration at any time during this period, during the infusion time, before we reach the steady state plasma concentration, equals the infusion rate, which is the amount infused per unit of time, usually mass per time, over the clearance of a drug multiplied by 1 minus e to the power elimination rate constant multiplied by the time. Or we can just substitute clearance by elimination rate constant multiplied by the volume of distribution. Okay, and later, after the steady state is reached, the plasma concentration at any time at steady state can be calculated simply by dividing the infusion rate over clearance, or infusion rate over elimination rate constant multiplied by the volume of distribution. And for the post-infusion period, the concentration post-infusion period, which is any point these after the infusion period, is equal to the C end, which is the last point just before the cessation of infusion, multiplied by elimination rate constant and by e to the power elimination rate constant sorry, by time post-infusion. Time post-infusion is any time that we wanted to calculate the plasma concentration following this point. So time post-infusion, normally we consider this as a zero time, and then we calculate the time that we wanted to calculate the concentration at which. Let's take an example. In this example, a patient is administered 60 milligram per hour 60 milligram per hour. So this is an infusion of theophylline. The pharmacokinetic parameters of theophylline are volume of distribution 40 liter and elimination rate constant 0.139 per hour. calculate the plasma concentration of theophylline in this patient after receiving the drug for 8 hours and at steady state. After receiving the drug for 8 hours and at steady state. In addition, calculate theophylline plasma concentration 6 hours after the infusion stopped. So during the infusion, which is 8 hours, during the infusion, the plasma concentration equals the infusion rate over elimination rate constant multiplied by volume of distribution. All this is multiplied by 1 minus e to the power elimination rate constant by time. We just apply the numbers and we get a plasma concentration of 4.24 milligram per liter as a concentration of a drug during the infusion time. For the steady state, we can just divide the infusion rate, which is 60 milligram per hour, over the elimination rate constant multiplied by volume of distribution, and we got a plasma concentration at a steady state which is equal to 10.8 milligram per liter. Then, to calculate the plasma concentration 6 hours after the infusion being stopped. So since we have calculated steady state plasma concentration, and we should know that the last concentration of a drug is the steady state plasma concentration. So if the infusion is stopped after 6 hours, if the infusion is stopped, then we have reached the steady state plasma concentration, and we can calculate the plasma concentration 6 hours starting from this concentration, which means that the initial concentrations that we have is 10.8 milligram per liter. We can apply this as C end, and then the time here is the 6 hours, and then the elimination rate constant is constant. We can simply apply the equation to find that the concentration 6 hours following the cessation of infusion is 4.7 milligram per liter. To consider your answer, you should be careful about the numbers that you got. Like here, 4.7 milligram per liter should definitely be less than the steady state plasma concentration, and during the infusion time, the concentration should be less than the expected steady state plasma concentration. This is a way to check your answer. Okay, effect of infusion and distribution time on the calculations of plasma concentration. For drugs that exhibit a short distribution phase after the drug infusion has ended, it is still possible to use one-compartment model intravenous infusion equations for the drug without a large amount of error. For example, gentamicin, tobramycin, and amikacin are usually infused over one half hour, which means half an hour. When administered this way, these aminoglycoside antibiotics have distribution phase that lasts about 1/2 hour. Note that if aminoglycoside are infused over 1 hour, the distribution phase is very short and serum concentrations can be obtained immediately. This means that for these drugs, for aminoglycosides, they need a distribution time in addition to an infusion time. So their distribution time usually takes around half an hour, and normally they given as an infusion over half an hour. If they are infused over 1 hour, then the distribution phase should be very short and embedded within the infusion time. So there is no need to consider a time for the distribution since it was considered already within the infusion time. Okay, so let's take an example to understand the case of aminoglycoside. Consider a patient is given an intravenous infusion of gentamicin 100 milligram over 60 minutes. The volume of distribution is 20 liter. The elimination rate constant equals to 0.8 231 per hour, and the half-life equals to 3 hours. Calculate gentamicin plasma concentration at the end of the infusion solution. So for aminoglycoside, as we said, it is an infusion equation. We can apply the rate of drug administration of elimination rate constant by volume of distribution with the rest of the equation. Direct application, and here we have the infusion rate is 100 milligram, and we have the elimination rate constant multiplied by volume of distribution. The time that we are going to use here is 1 hour, because in the question it said that the calculate gentamicin plasma concentration at the end of the infusion solution. Of the infusion, and here we have the infusion is over 60 minutes, so the time that we should use here is 1 hour, and the resulted plasma concentration at the end of the infusion is 4.5 milligram per liter. Okay, so for extravascular equations, where the drug is administered by other routes rather than the intravenous administration, here we should have an absorption phase and post-absorption phase and elimination phase. An example, this plasma concentration time curve is a typical plasma concentration time curve following oral administration of a drug. If we change the plasma concentration time curve to a logarithmic scale on a semilog paper rather than this representation on linear scale, we should get a straight line for the elimination phase, and we still have the absorption phase. The extrapolation of the drug, the slope of this straight line, we can find the elimination rate constant of the drug. This equation is normally used to calculate the plasma concentration at any time following oral administration of the drug. Well, time is the time after the extravascular dose was given, C is the concentration at time t, and F is the bioavailability fraction, Ka is the absorption rate constant, and D is the dose, V is the volume of distribution, and K is the elimination rate constant. I guess you remember the equations that we have taken in the subject of biopharmaceutics, and if you remember, there's a specific calculations for the absorption rate constant by residual method, for example. And for the bioavailability, we can just simply calculate it by dividing area under the curve following IV administration, if we have it, over area under the curve following area under the curve following oral administration, divided by area under the curve following IV administration, multiplied by dose after IV over dose after oral administration. Let's take an example for the application of this equation for the calculation of plasma concentration at any time following oral administration of the drug. Assume that a patient was administered 500 milligram of oral procainamide as a capsule. If you know that the half-life is 4 hours, the elimination rate constant is 0.173 per hour, volume of distribution is 175 liter, the absorption rate constant is 2 hours, and an oral bioavailability fraction is 0.85. Calculate procainamide plasma concentration 4 hours following a single oral dose. So the time that we wanted to calculate the plasma concentration at is 4 hours. So this is a simple application, direct application for the equation. Just be careful about the units. So we have here in milligram, and the plasma concentration should be calculated as milligram per liter, because we are going to use the liter of the volume of distribution. So the resulted concentration will be 1.3 milligram per liter. Okay, so note If the plasma concentration time curve displays a distribution phase, it is still possible to use one compartment model equations after an extravascular dose is administered. In order to do this, plasma concentrations are obtained only in the post-distribution phase. So the post-distribution phase is this phase. And here on this note, it assumes that we can still use, because on semilog paper, on a semilog paper, this should be considered as a two compartment model, because here, as you see in this figure, there's a distribution phase, and here is the elimination phase. We can still use the one compartment model phase for the calculation of concentrations anywhere following the distribution phase. Following this phase, any time point at these points at this time following the the distribution phase, we can use the one compartment model equations to calculate plasma concentrations instead of using the more complicated two compartment model, which will require the calculation of the alpha and the beta phase, and this is not quite practical in clinical practice. Note 2. The absorption rate constant is hard to measure in patients. Therefore, when only post-absorption, post-distribution serum concentrations are obtained for a drug that is administered intravenously, plasma concentrations can be calculated by the following simplified equation, which is just the introduction of the bioavailability factor on an open model IV bolus equation. This is because in a clinical practice, if we have a patient that has been administered an oral drug and we know that the drug was absorbed, the drug has passed the absorption period, and then we took a blood sample from the patient, measured plasma concentration of a drug for at least 2 points, and if we assume that the drug has passed the absorption phase and has passed the post-distribution phase, and the drug concentration now is in the period of elimination, for simplification of calculations, we can just consider that the calculation of the concentrations at these time points can follow simple one compartment IV bolus administration equation, just to consider the factor of bioavailability here by the introduction of F value. An example here is a patient receiving 24 milliequivalent of lithium ion as a lithium carbonate capsules. It is known that the patient has a volume of distribution of 60 liter and elimination rate constant of 0.058 per hour. The bioavailability of the capsule is known to be 0.9. Calculate plasma concentrations of lithium 12 hours after a single dose. Okay, so 12 hours is definitely enough for the drug to be absorbed and distributed. So the drug should be, according to this, should be in the elimination phase. And this can be simply calculated or estimated from the elimination rate constant by calculating the half-life of the drug. So direct application for the equation here, where the plasma concentration at 12 hours following the administration equals to the bioavailability dose over volume of distribution multiplied by elimination e to the power minus elimination rate constant multiplied by plasma concentration 12 hours after a single dose. So here we have applied 12 hours as a single dose, and then the resulted plasma concentration is 0.18 milliequivalents per liter. Okay, if two or more post-absorption and post-distribution serum concentrations are obtained after an extravascular dose. Volume of distribution, elimination rate constant, and half-life can be calculated by plotting and without plotting as previously described for IV bolus injection. One exception is that volume of distribution over F, or we call it hybrid parameter, is calculated instead of the absolute values of volume of distribution and the bioavailability. Let's take an example for this. An example, a patient is given an oral dose of valproic acid for 750 milligrams as capsules 6 and 24 hours after the dose. Valproic acid plasma concentrations are 51.9 milligram per liter and 21.3 milligram per liter. So following the administration, 6 hours and 24 hours, plasma concentrations are 51.9 and 21.3. We can plot this plasma concentration on a semilog paper to get 51.9 and 21.3. So we just draw a straight line between this point, 21.3 and 51.9. This straight line represents the plasma concentration time curve. We consider this straight line as a similar way as we have calculated the plasma concentration following IV bolus administration. We assuming here that the drug has passed the absorption period and the post-absorption, post-distribution, the post-distribution phase, and these drug concentrations are taken within the elimination phase. So we can just simply calculate the elimination rate constant or half-life of the drug and volume of distribution by the simple plotting area. Okay, to calculate the half-life of a drug, we can divide one of these 2 points, either the 51.9 milligram per liter to 2 or the 21.3 to 2. It's more simpler to divide 51.9 milligram per liter to 2, and then the resulted concentration is 26 milligram per liter. We can just draw a straight line from 26. So this is 20, 26 is here. We draw a straight line until it hits the plasma curve, and the time here is 20 hours. The difference between 20 hours and the 6 hours for the first point is 14 hours, and therefore the half-life of the drug is 14 hours. We can just simply calculate the elimination rate constant. Okay, again, by the extrapolation of this straight line to the y-axis, we can find the value hybrid constant or the volume of distribution over F. First, we find the plasma concentration at time 0, which is here in this case 70 milligram per liter. Then the hybrid value is dose over plasma concentration at time 0, which equals to 10.7 liter. And again, also we can do the calculation method without plotting here by calculating the slope, logarithmic scale of the points, these 2 points, and difference between their times equals to minus 0.0215, and then we can simply calculate elimination rate constant, and also we can calculate the half-life of the drug. You can see here that the same results we got using the calculation method as compared with the plotting method. Again, we just calculate plasma concentration at time. The F value. Here we can just find the plasma concentration at any time. Rearrangement of this equation, we have found the dose over plasma concentration multiplied by time, and this will give us a hybrid value of 10.7 liter. Okay, So if we take a multiple dosing and steady state, the previous method of administration were for drugs that are administered by single dose, whether IV bolus administration, infusion, or even extravascular routes like oral administration. Here, we should consider that in practice, drugs are mostly administered as more than one single dose, usually multiple doses. Uh, in case of multiple doses and the steady-state equations, in order to change a single dose equation to the multiple dose version, it is necessary to multiply each exponential term in the equation by the multiple dosing factor. So the multiple dosing factor is 1 minus e to the power n, which is the number of doses, by ki, which is the rate constant found in the exponential of the single dose equation, multiplied by tau. So this tau is the time interval. Similar applies here on the other side of the equation. At a steady state, the number of doses, which is n, is large. The exponential term minus nk to multiplied by tau becomes a large negative number, and this value approach zero. Therefore, the steady state version of the multiple dosing factor becomes the following: 1 over 1 minus e to the power minus k multiplied by tau. Because here we assume that following multiple high number of administration of doses, definitely the drug will be able to reach a steady state plasma concentration. And at steady state plasma concentration, since this number becomes very high, then the value will be approached to zero, and therefore the equation can be rewritten, or this factor can be written as this. These are a list of equations that are normally used following single dose, multiple dose, or steady state following different routes of administration. Here we have intravenous bolus, we have continuous intravenous infusion, we have intermittent intravenous infusion, we have extravascular route, and we have average steady state concentrations, any route or administration. You can see the differences between this factor introduction and then the conversion of this factor to this following the administration of a drug, or following the drug that has reached the steady state plasma concentration. Same apply to all other equations. These equations are not necessarily to be memorized. We normally provide these equations with a question paper for your application in the exam. Okay, more equations at which we can find different pharmacokinetic parameters according to the method of administration and according to the status of administration, whether single dose, multiple dose, or at a steady state. You can see that the pharmacokinetic parameters are different at each of these points. It's, by the way, it's not necessarily to provide these equations. You should be able to memorize the simplest these equations as they are simple. Maybe except for some of them, it might not be easy to memorize. So we might provide these equations as an appendix with your question. Okay, so we comes to the designing of and individualization of dosage regimens. We can use here using one compartment model equations. To design an individual dosage regimen, it is important to know that the therapeutic range or the effective concentration of the drug. It is important to know the therapeutic range or the effective concentration for the drug. One compartment model equations can be used to calculate dosage intervals, tau, and maintenance doses, and loading doses, as follow. For the calculation of tau, maintenance doses, and loading doses, it is different according to the route of administration. For example, in intravenous bolus, tau equals to natural log of a maximum plasma concentration minus natural log of minimum plasma concentration at a steady state over time. For the maintenance dose, it equals to plasma concentration at a steady state, maximum plasma concentration at steady state, multiplied by volume of distribution and multiplied by 1 minus e to the power elimination rate constant multiplied by tau. This is for intravenous bolus. For the continuous intravenous infusion, the calculations are different. For intermittent intravenous infusion, the calculations are different. And for extravascular post-absorption distribution, also we have the introduction of the bioavailability factor here in the equations to be considered, and also for the average steady state concentration at any route administered, the equations are different. Again, you don't need to memorize these equations. We can simply provide them as an appendix with your examination paper. Okay, so multi-compartment models. Through the previous slides, we have taken or described the one compartment model, and also we considered the two compartment model for some drugs at which the distribution phase is very short, and for simplification we have justified the use of one compartment model for the calculation of plasma concentrations. For the multi-compartment model, assumes that the body composed of more than one compartment, usually a central compartment and peripheral compartments. A two-compartment model is the simplest of the multi-compartment models. The drug that shows by exponential plasma concentration time curve is said to follow the two-compartment model. And when we say by exponential, it means it has more than one expression, it has more than one straight line through the plasma concentration time curve. Here, for this drug, it has around two straight lines, this one for the distribution phase and this one for the elimination phase. So this plasma concentration time curve is called bi-exponential, which is a representative for the two compartment model rather than the one compartment. Multi-compartment models are rarely used in patients care situations because it's difficult to apply the pharmacokinetic parameters and get an accurate result. Here, for simplification, we normally use the the one compartment open model. If a drug follows multi-compartment pharmacokinetics, serum concentrations are usually not drawn for clinical use until the distribution phase is over and the elimination phase has been established. In these cases, once the distribution and the absorption phase are finished, then it is possible to use simpler one compartment model equations to compute doses with an acceptable degree of accuracy. And it will not be very accurate, but for the clinical practice, it will have enough accuracy. It will have enough accuracy for the clinical application. Non-compartment analysis is the most commonly used technique of pharmacokinetic data analysis directly from plasma concentration data without the need to assume that the drug disposition follows compartmental model. When we say disposition, it means distribution, and elimination of drug follows compartmental model. In this technique, the non-compartmental analysis, as we said, we can use the plasma concentration time curve to calculate the pharmacokinetic parameter. An example is to calculate the pharmacokinetic parameter. We should first calculate area under the curve in the plasma using the plasma concentration time curve. For the calculation of area under the curve, the PK parameters reflecting the exposure of the drug. It can be calculated by trapezoidal rule by assuming that the area under the curve is the sum of several small trapezoids. So these are trapezoids that are composing the total area under this curve. By simple calculation, summation of the area of each of these trapezoids, we can calculate the total area under the curve as follow. So if we consider that we have a plasma concentration time curve, it is not necessary for the calculation of plasma concentration time curve to plot the data on a semilog paper. There is no need for this. So in this case, we consider that the plasma concentration time curve is composed of multi-trapezoidal shapes, each of them in the corners of these trapezoidal shapes is the differences between 2 points. So this is the first point that was measured, and here's the second point, and here's the time differences between these 2 points. So for the calculation of this area of one of these trapezoidal, let's take this as an example. The area of trapezoid, as you know, is the summation of 2 lines divided by 2 multiplied by the height of the trapezoid. So if we consider that the height of the trapezoid is the time interval, and these 2 lines, which is line for the line here and line here, are summated and divided by 2 and then multiplied by the height, we can find the area of this trapezoid simply then by collection of all summation of trapezoidal areas for all of the points that we got. We can get the area under the curve from time 0. It's not from time 0, by the way, since we didn't consider the initial plasma concentration at time 0. And then from time of first point until time of the last seen point. So the equation will appear as this. The total area under the curve will equal to plasma concentration plus plasma concentration just before the point, and the plasma concentration of the point divided by 2. These values represent the 2 lines that compose of the trapezoid, dividing by the height, which is the time difference between these 2 concentrations areas. And then summation of all of these trapezoids will give us the total area under the curve from time 0 to time of last seen point. For the calculation of area under the curve from from the last time point to infinity, we can just divide the last concentration of the last seen or observed concentration over the elimination rate constant to calculate the time from last seen point to infinity, and then simply add this area to the rest of the area and to get plasma concentration from time 0 to infinity. Okay, we can use the area under the curve for the calculation of clearance. So clearance can be determined directly from the plasma concentration time curve by dividing dose over area under the curve from time 0 to infinity. It is important to consider time 0 to infinity. It's not acceptable to calculate area under the curve from time 0 to last observed point and then use this value to calculate clearance. Clearance can be calculated based on area under the curve without the need for the assumption of compartmental models. Okay, half-life also can be calculated in this way. The half-life of elimination can be determined directly by plotting actual concentrations on the similar graph paper. Other method for the calculation of half-life is through the estimation of the slope in the plasma concentration time curve using the following equation, which is the equation that we normally use. The selection of the time points from the plasma concentration time curve for the calculation of the slope is crucial in the determination of elimination rate constant. The last few points of the curve represent the elimination phase, therefore the slope should be determined from the elimination phase by using at least the last 3 points of the curve. This is very important because in the plasma concentration time curve, the last points represent definitely are part of the elimination phase. So it is not acceptable to use points that are involved in the distribution phase to be used in the calculation of the elimination rate constant. Usually use in your calculation points or points that are within the last 3 or 4 points, and try to avoid, not try, definitely you should avoid the use of any point that is close to the distribution phase. Otherwise, your slope will be completely different, and then your elimination rate constant will not be accurate.